first. Okay, now it's on the record. What I would like to do is that, you still we have this example number 1 that I should like to explain some point. But before that, let me only give maybe 10 minutes or so on this, because I want to cover another thing as well. So, okay. When we look at the system, okay, I really don't think it's a good idea much to call that one B1, because if you take a closer look, you see that this B1 will have to extend out and give the support to B2. When you look at the beam B2 itself, you see that the beam B2 here doesn't have the support. Okay, so this is the technique that I wish everyone takes my class who know. We have a case where the two corners, this corner is met by two beams. Okay, so you see, if you look at B2 itself, there is no support directly from any beam, right? So, and as we speak now, there is no support for B2. So we need to provide two supports for B2. And then when you look at another side, there's also this beam. I don't even have the name for it. 1, 1, 2, 3. So let's call that one B4. Right now, B2 and B4 do not have any support. So when you look at B2 and B4, if you don't look at the whole picture, you would probably be inclined to think that this should be the point where you can have support. But in fact, who's going to support who? See, this is the corner of the overhanging portion of the structure. It is not the corner where, you have the typical stuff like the columns are here, and then you have the corner, and then beams meet at the corner. This is typical, right? But when you look at this particular corner, it is customary not to use this corner as the support for each beam. Each beam in this case means B2 and B4. So, what's coming from the chat? What's that? Okay, anyway, when you see the corner like this in the real building, what you need to do is just to try to locate the support for B2 and B4 first. But B4 would have to be supported by the cantilever portion coming out of this column. So these 2 points will be the support for B4. This is also the support for B4. Okay? And for B2, the support for B2 would have to be this, of course. Doesn't seem to help much. So, it's okay. I'm just using this one. This one will be one support for B2, and then another would be this one. So the two supports for B4 would come from the overhanging portion of this B1 and then this B. And then your B2 will look like this. With this is the support, and then that is that support. And this is a cantilever portion out of this one that does not support B4. And when you look at B4 now, I have to erase this, it gets in the way. Okay. When you look at B4, the free body diagram of B4 will be like this. Okay, that means when you look at this end does not support B2 either. Let me write this down for you. This overhanging does not support B4. I'm sorry, B2. And likewise, this also does not support B4. In other words, we engineers tend to make this portion and that portion strong enough to survive by themselves. Okay, so we would design so that this portion can carry the moment from the overhanging portion and strong enough without the help from B4. And likewise, we'll design this portion of B4 to be strong enough to survive by itself without the support from B2. So that means the uniform load on B2, this W will be equal to the floor load plus the weight of the beam. So let me try to write down here. This W is going to be equal to, we have here 600 and 1500, right? So it's going to be 600 plus 1500. Now the tributary width for B2 would be this. So it's half of 1.5 meters, or 1.5 meters over 2, plus the self weight, which is right here, 500 kilogram per meter. So that will be the W acting on B2. After the analysis, you would find that you would have the reactions of B2. Say this one, the pink one, and let's say the green one. The pink one will act on this beam B1 with a cantilever portion. And then the green one will act on this beam. Okay, so that's how this structure works. You see, another special thing is that this beam is not a simple beam. It's a continuous beam, but I'm not asking anyone to analyze it, but you should know that that's a beam with 2 spans and then a cantilever. Okay, so is there any question on this one?
มีนมค่ะ
Right. No, okay. I have a question that both overhanging are at the same level and they are connected. They are the same level, but in construction wise, they are connected, but they don't take the load from each other. You don't need to leave the space there for them not to carry each other. When under construction, you just need to make them connect. But the details of the reinforcement or the details of your structure will dictate the behavior of the structure. Because if you make B2 here so strong that it can take the negative moment here and so, you know, it's just going to survive by itself. And then B4 is the same. But, you know, this is the one that I wish to talk about, because some of you would think correctly that, for example, from this picture, B2 would have to sit on B1, something like that. But in the construction world, yes, B1, the cantilever portion of B1 will have to support B2. But in the real construction, it doesn't mean that you have to put B2 on top of B1 so that B1 can support B2. You can put every beam on the same level. You know, you go back in your house and look at the structure. You don't see one beam sits on top of another, because if you do that and you stack the beams up, you know, the overall depth of your system will be humongous and architects will die. You know, they die because of that, because they're so mad, right?
Question, sir.
Yes, please.
If you said that the two beam is connected, and if I draw it accurately,
yeah, it just may have to look like that.
Yeah, there's always a weight of this portion. So where it goes?
You know, this is a very good question, because in the real world, you know, that is something that we cannot say precisely calculate. So we have to, you know, make the assumption that is good enough for us to handle the calculation on every level. Because, for example, you guys have had the trust lesson, right? With Ajahn Julaport, correct? Am I correct?
Yeah.
Do answer me, please.
Yes.
Yes. So let me show you this. The truss. You know, let's say a simple truss like this. I don't know if you have asked Ajahn Julaport like this in the class. Let's see, put some load on it. We assume that the truss is a two-force member, correct? So that means in all of these members, there's just one axial force. So let me ask you this. Does the truss member have a weight? Yes or no?
It has.
It has, yes. It can float in the air, can it? So what kind of load is the self-weight? It's a uniform load, isn't it? So that means we're going to have a small uniform load like this on the member, aren't we? We do. There's no denying that. So how can we have a real trust in the world? We don't. We would never have a trust as a two-force member that you discuss and, you know, learn in the statics class. No such thing. Think about it. But we can neglect this because it's so small. But you cannot always neglect the weight of the member of the trust. Can we? Have you seen the mega trust at the mega, whatever that is, name the Muang Thong Thani, right? Have you seen it? The mega trust? Have you been to Thong Thani perhaps? And you see that?
Yes.
Yes, some of you haven't. I said no. Okay. So let's say some trust member can be as big as, my height, like 2 meters in depth. When you have the member that big, the weight becomes part of the analysis. And in that case, you will not have the typical trust as a true false member anymore, because the weight matters now. But in the typical case, like the trust in the roof system, that trust has small members. Yes, it has weight, but we can say, I don't care. We're going to neglect the weight of the member because we can. That negligence doesn't cost us anything because the weight is negligible. But when you're dealing with the big trust, you can't neglect the weight anymore. It's just the same as what you've asked. Yes, 2 beams coming in at one corner like this. We can, say, analyze the beam by simply using this line of action, the center line, and say, okay, we're gonna analyze this beam and we're gonna analyze that beam, the pink ones. Okay, it doesn't matter much because what we do not account at this corner, just like so tiny. As long as you connect them right, it's like if this is a concrete beam, as long as you have the reinforcing steel through the end like this, things are gonna be okay. But I like your question. It's like you have quite some perspectives, looking at things. So please, anyone, if you have any question about anything, fire them away so that we can have discussion. Okay?
Sorry, teacher.
Yes.
What about timber?
What about it?
Timber.
Yeah, what about it?
Oh, okay. For a style of the connected between in the corner, sometimes I see that it will cross it up and it will be combined together in like a.
If they are combined, the corner,
which should not to be intersect together.
Maybe.
But in the ancient, there are some techniques. Yeah.
True. Because my old house is made of wood as well, and at that because you cannot. It's going to be more difficult for the old technology to put the wood on alongside each other. So in the floor joist system made of wood, we tend to put the joist on top of the main beam. That's the case. But if we meet at the corners, maybe at my old house, they come together and join at the ends, and it's the same concept that we need to have like members that strong enough by themselves to carry the load. It's the same, but how they meet at the end, it sometimes depends on the technique. I can say non-structural technique to just make the ends look. You just need to.
Oh, that means you need a tiny point, right, to consider.
It is sometimes.
Okay.
That's what I was trying to say at the beginning, saying that what about it? Maybe if you have details and show it in the class, everyone can see, including myself, we can discuss better.
Oh, sure. I will bring a folder.
Sure. Please, anyone is welcome to bring something like this to the class so that we can see things together. I need to put on this earphone because now my kids are here and then they're making noises from the commotion. They're having lunch now. Yeah. Fun, right? Taking care of the kids, taking care of the students, taking care of myself. And today I don't have to receive any mailman because they come earlier, come before the class begin. So that one burden gone. It's got so tidy, excuse me, I'm wasting a minute in trying to unravel this. Okay. So, is there any more question regarding this?
Yeah, I do have. Can you please jump to the drawing page?
The drawing page.
That the corner that you draw. Yeah.
Okay.
You say that the highlighted portion is small enough to be neglected. Then what if, as far as my understanding, in our analytical model we use only center line, but what if the width of the beam as it is a very big wide beam, then this portion will get bigger. Then
but when you analyze the beam, you know, even if the portion becomes so big, it's still part of your beam and it's part of your self weight, correct?
Yeah, but then what if this portion is big? It is still negligible.
Yeah, it's possible, but in that case, you can, I don't know, because let's say even if this portion is neglected because your drawn pictures on your machine, so I don't know if I can just respond to that. Okay, that portion. No, I am guesstimating this on my iPad. This portion is big, but as long as we can provide reasonable reinforcement here, it's gonna stay, you know. And no matter how big this is, comparatively, this length that you have compared to the entire length of the beam is still pretty negligible, right? Don't you think? So the moment generated by this length is minimal compared to the moment generated by all this. And this width, if it's an RC beam, if you have a band beam like this, they call it band beam literally. As long as you provide the reinforcement at the corner, they're gonna stand. You know? It's our job to dictate the behavior of our structure, and it will behave the way we want it to be behaving. So even if you have like the large portion of that, you can always give details to your beam so that it would work, you know? So now it's not completely part of the analysis, but you know, giving proper details for construction is also part of our job. So that would be involved in the details part. Okay. Right.
Crystal clear.
Crystal clear. Thank you. Okay. So now what I wish to go over in this. Now I'm trying to use the mouse with iPad. I made some time enough. Okay. So here we go. I wish to stop discussing about this plan here, and I'd like to bring you to this. Now I have an ant on my iPad. Okay, it's a drop of water. I'd like to bring you to this one more example about something. I'd like to give you this scenario on the problem, because this is the reflection from the industrial sector saying that they want you to truly understand the behavior of the structure, shear force diagram, bending moment diagram, and such. So I always, in the exam, give you the beam, give you the shear force diagram, give you the bending moment diagram. But chances are I give you the wrong diagrams. These wrong diagrams may come from the situation that you ask your junior engineers, you know, to run the beam for you, to do the analysis of the beam for you, and then they made a mistake. But for you, when you look at these diagrams, you should be able to tell what kind of mistakes they made, or if there are any mistake in the beginning. So when you look at this diagram, a part of my question would be something like this. Are the results correct? Most of you will be able to answer that they're not correct. But the next question is this. What are the errors? Now, the reason that I bring this to the class, it's because most of you would not get this right because you don't understand the question. The errors of what you would answer, shear force diagram is not correct. Of course, we know that it's not correct. But what is the cause of that incorrection? I don't think that's that word, you know. What is the cause of that error? What caused your shear force diagram to be incorrect? That's what I look for in this question. Okay, so if the results are not correct, if not, what are the causes of that error, of those errors, or that error, one error, two errors? Like this, for example, you see that in this case, the shear force diagram, they're wrong from the beginning. Simply because when you look at this, that shear is coming from 1.5 to minus 0.5. So the total change of the shear here is 3, right? 3 tons. So in this, you want to get this from the beginning because I get this because I made it. Okay. So, but when you see this, if you have sharp eyes, you would see that, okay, this is 3 tons and this is 2, right? This is 1.5 tons per meter. 2 multiplied by 1.5, that's 3. So meaning the shear force diagram here is not correct. And the error is that somebody who created the model to analyze this forgot this small uniform load. So the answer to this particular question is that the error is made by, you know, this uniform load has been missing. So that is the question, that is the answer that I'm looking for when I ask you what the errors are. Okay, not because, you know, results are correct because the shear force diagram is wrong. That's not the answer. That's not the in-depth analysis. Okay. And this happens in the real world because I have told you before that when I was young, I tend to forget the loads like all the time. But okay, like but I don't have the case here. See if I could give you the example. No. Anyway, but you know, anyway, my favorite error is this. When I have the beam, the main beam, that support secondary beams like this coming in, secondary beams coming in like this. But they generally they come in from both sides. But I always calculate the load based on just one side. So instead of having the reaction from this beam, and this beam, and then this beam, and then this beam, and then this beam, I have the reaction from one side. So I miss the load, not much, just by 50%, you know. And when you miss the load by 50%, generally that means disaster. Okay, so we need to be able to see things like this because I have to say this, it's only natural that you make a mistake. Everyone will make a mistake from time to time. But when you make one, you must realize that immediately. there must be the knowledge enough in you to see the results and see that is not correct. Something that is we can call that sense. It's a sense like this. It happens every year, and you can laugh now, but you may not laugh when it occurs to you like this. I can draw a triangle like this, and when this angle is 45 degrees, when it's 45 degrees, this side is equal to that side, right? That's why we have 45 degrees. So the sine and cosine, they must be equal, right? And yet, in structural analysis number 2, when we have to use the trigonometric function to form our metrics, I see it every year that someone would have the sine and cosine not equal when the angle is 45 degrees, for example. You see, that's kind of nuts. And you should know that the basic relationship like this: the sine square plus cosine square is equal to 1. So the term sine square and cosine square will never by itself be equal to 1 or greater than 1, right? It has to be less than 1 always, because sine and cosine are both less than 1. So when you square it, the number should get smaller. It's common sense. When you look at numbers, you should know right away, this can't be correct. So it's the same thing. We are trying to move that kind of sense into, you looking at the results from the analysis of the beam as well. So I will give you this practice for the active session number 2 that we're going to have on Friday as well, and we are going to continue on with the load transfer stuff, because we have more problems. You can choose to carry on with that, and you can try to work with this kind of problem as well. Okay. I think what I would like to talk about, the example number 1 should be enough. So please feel free to go on and perform your analysis by yourself. Okay. And please take a look at the one more thing. This is B3. So basically I have written about B3. This is B3, pretty similar. So for this, let me try to draw the free body diagram for you. This is not something you can analyze yet, but you should know that when the beam is continuous, there's no point trying to draw a simply supported beam. Your B3 would look like this, okay? With the point loads coming in from this and from that. And then you have the reaction from B4. Like that. And then you have the self weight of the beam throughout the length. But that's not it, because don't forget that you also have this area of the floor that your beam B3 must support. So you also need to include the self weight starting from the second column through the end. Okay. So that should be it for today. So is there any question? Hello. Is there any question, folks? Hello. Is there any question? Oh, so we have a question in chat room. At this moment, no. So that means we are pretty crystal clear, right? So let me stop the record.